Okay, so we're still talking about the properties of the photoreceptors so that we can go through this process of transduction and change the light into something the brain can understand. And because we're still in the middle of that, I am bringing us back to this summary slide so that we know where we are. We've talked about the photoreceptors, the rods and the cones, that they are two different kinds of photoreceptors, that they are different in their appearance, their distribution, their wiring, which influences their acuity or their ability to see detail, as well as their sensitivity, so their sensitivity to dimmer light. And we are about to start talking about the clinical issues, and then we'll get to functional significance. So I'm going to start by talking about the clinical issues. And if we look at the clinical issues and the wiring, they actually inform us about the functional significance. But I'm going to talk about that explicitly as well. It's all kind of wrapped together in how the rods and cones work and what they give us. So we have different clinical issues depending on whether or not we are losing our rods or losing our cones for whatever reason. I'm going to first show this picture that kind of tries to show you what it's like if your cones are deteriorating. So the cones are giving us color vision, as we're going to get to in the functional significance, and they're giving us that acute vision. They are making up the fovea, so we really lose that foveal vision. And this is called macular degeneration. Macular is the macula is kind of around, including the fovea and a little area just around that. And this occurs as we age. So if we live to be 80, 90, 100 years old, it's pretty likely we're going to have some macular degeneration. There are ways to influence it. So taking our omega-3s, taking our zeaxanthin, and our lutein, so those carotenoids, or just eating the fish that gives us the omega-3s and eating the green leafy vegetables that gives us those carotenoids can really help us to maintain a healthier pigment epithelium so that we do not see this deterioration quite as quickly. Once we see this deterioration, whatever we've lost, those cones that we've lost are gone. We're not going to get them back. And so many of your grandparents are probably going through this kind of loss of their vision where they're looking, and that really acute vision, and it's probably getting a little bit more black and white for them. Retinitis pigmentosa is a really different kind of condition where the rods deteriorate, and this is genetic, and most of us don't have to think about this or worry about this unless it's in our family. And if it's in our family, as far as I know, once it starts, I'm not sure if there's anything they can do at all to slow it down the way there is for that macular degeneration. But since they're losing their rods, the picture on the left is kind of a quote normal vision, and then on the right it's showing retinitis pigmentosa, but really what's happening is not quite a just blackening out. It's more of a just real blurriness because all of those rods that are in the peripheral vision are gone. And I'm going to tell my little story about retinitis pigmentosa. So the very first time I taught sensation and perception, I taught it for an introductory psychology class at Midlands Technical College, and I was teaching night school. And I had this older woman in the class who really kind of, I saw her just change when I started talking about retinitis pigmentosa, and she just did this, my son has that, my son has that. And she told this story, right, which is a story on herself that is maybe a little bit embarrassing. But she told me that her son would not pick up his toys. She would tell him to pick up all his toys, and he would pick up like a few of his toys, and then he would say he was done. And she would point out to him, there's some over there, there's some over there, there's some over there, you missed all these toys. And so she took him to the eye doctor because he kept saying, I just don't see them, I just don't see them. She took him to the eye doctor, and the eye doctor said, well, he has this retinitis pigmentosa, and it's kind of like, it is a tunnel vision. He cannot see those toys. And she told the doctor, the eye doctor, he's playing you. Yeah, she didn't know the boy's father for very long. He was part of her life, but not throughout the boy's life. And he was actually, I want to say he was in high school. And she brought him in one night to talk about his retinitis pigmentosa, because whenever I can, I have students share. And before we got to him talking, he decided he wanted to take a walk around Midlands Tech, and he needed to do that before it got dark. And as soon as it started getting dark, she kind of did this, I have to go find him, because it's not just our peripheral vision, it's also our night vision, as we're going to get to. If we don't have our rods, we can really only see during the daytime. So this boy was never going to drive at night. This was a pretty severe retinitis pigmentosa, because since he already could not see at night as he was in high school. Sometimes it happens like quite a bit later, but we see this deterioration of the rods, and sometimes it's severe enough to where they start to lose their cones as well, and so they just go completely blind. And again, that's genetic. We're going to get macular degeneration most likely as we age, unless we're very healthy. And if we get to ages 90, 100, 110 even, it's pretty likely we're going to see some of this macular degeneration, no matter how healthy we are. The final clinical issue to talk about here at the back of the retina is a detached retina. So this is the pulling off. So what my picture is showing here again is that we're getting that information back to the retina, and on the back of the retina we have those rods and cones at the very back, the neurons, the bipolar cells and retinal ganglion cells. The light is coming through the optics of the eye, the aqueous humor, the vitreous humor, and through all those neurons to hit those rods and cones. And behind that, behind the rods and cones, you'll see that dark, almost black band that is showing the pigment epithelium. And what happens with a detached retina is that the rods and cones are basically ripped off of that pigment epithelium. And this is typically environmental. So I was warned about sleeping with my dog, because sometimes your dog, when you sleep with them, they might put their paw against your eye and pull it off. I've also been warned. So these are the warnings I've lived through. I was playing racquetball with a friend and I wasn't wearing goggles, and another friend of mine told me he's pretty dangerous with the racquetball, and if you're not wearing goggles, you might get a detached retina, because that ball could hit your eye and pull the retina off the pigment epithelium. As I've aged, so I'm 50 now, and I am extremely myopic, and apparently it is because of my long eyeball. My eye doctor has told me that just because of the shape of my eye, I'm more likely to, just by nature, have a detached retina over time. So it is environmental, but it can happen because of other issues with the eye. And again, here what would happen is, because those rods and cones are ripped off of the pigment epithelium, they can no longer regenerate. So we're going to go through how they go through transduction, and that they have to regenerate in order for us to use them again at all. So if they've been pulled off and they cannot regenerate, they're basically, you can call them dead. What we do now is there is a surgery. If I have a detached retina, and they can surgically connect the retina or the rods and cones with that pigment epithelium quickly enough so that we can regain that eyesight. But for someone who's had the detached retina and they haven't done that quickly enough, or they did not get the surgery, they're just missing their vision completely in that part of the eye, because the rods and the cones aren't regenerating. They're not doing their job at all. It's like a huge blind spot. So here's my circuitry again, as we've talked about now a few times, and this is usually where I ask for questions, so maybe pause and think about if you have questions. Maybe pause the recording and think, are there questions that I have for the next coming Monday when we can actually talk with each other? Because I think a lot of this is pretty complicated. it's going to stay pretty complicated. And as we talk about transduction, and you really need to understand the pieces and parts to move on to the bigger pieces and parts. So I'm going to give you the basic structure of the photoreceptors that allows for this transduction to occur. As I keep saying, this is the changing of that electromagnetic energy into electrochemical energy that the brain can understand. This is what the rods and cones are doing. I'm going to give an example from of a rod, but the same kind of thing is going on in a cone. So the basic structure of the rod photoreceptor, you can see the inner segment there, the outer segment, and a synaptic terminal, where the inner segment, so if I'm looking at this left part of the picture, the inner segment, you can kind of see the little amoeba-looking thing is my cell body. The outer segment is the upper part of that in our picture, which has these stacked discs, and then the synaptic terminal is at the very bottom. And so remember, light is coming, in this case, from the very bottom. This is the outer segment there is at the back of the eye, through all that stuff, coming into the outer segment, but we need to get it back out. We're going to communicate to the bipolar cells and the horizontal cells so that we can get that information to the brain. And so that synaptic terminal is going to do that communication. The outer segment, again, it contains those stacked discs, which you can kind of see in the picture, and then Goldstein magnifies a little piece of that to show the stacked discs. Each disc contains thousands of these visual pigment molecules. So that thing on the right-hand top that looks kind of like a tack, that is a visual pigment molecule. And if we magnify that, what we really see inside of that as the visual pigment molecule is this long strand of opsin. So you can see it snaking across this, and it's going across the membrane. So those little stacked discs are, made up of these membranes that separate them. And that opsin is snaking across that membrane 7 times. And part of what's important about that is that little tiny blue dot at the very, very right part of it. I was hoping to do this on Monday where I could circle it, but that's the retinal. The opsin and the retinal together are what makes up rhodopsin. That's the visual pigment molecules, what we see in the rods. There are different names for that in the cones, but for the rods it's called rhodopsin, which really means it's red. Has a red pigment to it, looking pigment. So I'm going to unpack that each visual pigment molecule is made up of 1 opsin and 1 unit of retinal. Okay, so the opsin is remember, if you go back to the previous picture, it is the long piece. It is this long protein that is snaking across the membrane 7 times. It's very long. And what is being shown in this picture is just a very short little piece of that opsin. The piece that has the little retinal. So if you go back to the previous picture, which I suggest that you do, and go look at that now. You go back to the previous picture. There's the opsin, and it's shown in kind of a pinky color, and it's going across the membrane 7 times. And on that is 1 tiny molecule. Just one of those molecules is retinal. Okay, and what this picture is showing is the retinal is basically what we're looking at. And that, if we're looking at this molecule in the dark, we're looking at the left-hand side at what's an A, and that retinal is kind of bent over. Okay, and what happens is when we go out in the light, the retinal is going to isomerize, it's going to change its shape because it's in light and it's responding and saying, yes, there's light out there, right? It's going to change shape and it's actually going to break off from that opsin. And remember, that opsin is, we're showing a little tiny segment, but it's really very long. It's the long part of what we saw in the previous slide. So I'm going to walk you through some of this is repeating, but with the various pictures and getting it to the last part of causing transduction. So the rod actually fires after all of this. Remember, if we're looking at those outer discs, those visual pigment molecules, those outer discs have, each of those discs has thousands of visual pigment molecules. We're looking at this snaking opsin, this really long protein strand, and that little tiny blue dot in the upper picture, that little tiny blue dot is retinal. You can barely see the word retinal. That light, so we get one photon of light into the eye, and it's absorbed by that retinal. The retinal undergoes isomerization, that changing of shape, so it isomerizes. We saw that in just the previous slide, if you want to go back to that, where we're looking at a little tiny piece of opsin and the retinal that starts out kind of bent over and it straightens out. Okay, and as I said, that bond, actually it breaks off. The bond between the opsin and the retinal is broken, and that causes this enzyme cascade. Okay, all of these enzymes influence other visual pigment molecules, and then we see another sort of cascade beyond that, and you can think of it as fireworks. And so the picture at the bottom is showing this kind of enzyme cascade so that the entire rod fires. All we need is one photon of light, one retinal isomerizing, and the entire rod is going to fire because of this enzyme cascade, those enzymes acting as messengers. So the photoreceptors have just undergone transduction. I'm going to walk through it again. It causes this visual pigment bleaching. Okay, so what's happened is, I'm going to start with the picture, actually, at the bottom right. What we start with is, at the bottom right, an A, even the very bottom picture there, you can see that it's reddish. The red color, that is a frog's retina, okay? And if you see in the picture above that, the opsin, we see the retinals kind of bent over. If you remember, this is how we start. And then we get a photon of light. A photon of light allows the retinal to absorb the energy. The retinal absorbs the energy. It changes shape, which we see in the top picture in B. Changes shape. It breaks off from the opsin, which we see in the top picture of C. And that breaking off from the opsin triggers an electrical event such that we have transduction. The whole rod fires. And what the bottom pictures are showing in that is the frog's retina. It has rods, and if you remember the rhodopsin, the RHOD of rhodopsin really stands for red. And we see this visual pigment bleaching. If the frog goes from dark to light, we see this bleaching of the retina as all of those rods are bleached. So for us to use those rods again, for us to use those photoreceptors again, they have to go through this visual pigment regeneration, okay, which it takes enzymes from the pigment epithelium. So remember, if we have a detached retina and we've pulled off those rods and cones we've pulled it off from the pigment epithelium, they cannot regenerate, they cannot be used again. They've performed their transduction and they're done. But what happens is there are enzymes provided by the pigment epithelium that are a catalyst for the retinal and the opsin to reunite and for this to all come back together so that we can use that rod or that cone again. In this case, we're looking at rods. That visual pigment regeneration, it takes time. Okay, it takes 6 minutes for cones. It takes 30 minutes for rods. And we're going to see what this means for our ability to adapt to the dark in just a minute. So our dark adaptation is very much informed by all of the information that I just gave you, but we're going to go through it again. I know that we're going through this in different ways from different perspectives, but dark adaptation is basically that time it takes for us to see in the dark after we're in light. And I usually think about it as that I walked into the movie theater late, where I'm coming in from the light from the outside. We walk into the movie theater and it's dark and it's hard to see. And actually, we usually wait for something to come up on the screen, right? But if the screen is also really dark, it takes us a while to adapt, right? So our ability to adapt and to see it takes time. And we're going to look at these dark adaptation experiments. If you remember me talking about the classic psychophysical methods, that method of adjustment, we've used this to tell us about the mechanisms of the eye. We're using the method of adjustment. So what the person is doing, so this picture at the bottom right, the person is looking at the fixation point, okay? There's light in the surrounding room, and we're going to turn that light off. And also there's a test light. So that dashed line is showing that there's a test light off from the fixation point, and it's that it's hitting a different part of the eye that's a little bit off from the fovea. What this means is, for this person, that test light is hitting both rods and cones. Remember, we have cones in the fovea, and if we see normally, we have rods and cones in the periphery. And we're going to measure this adaptation to the dark and the time that it takes to adapt. Okay, so what happens when the person is looking at the fixation cross and that flashing light is over in the periphery? What we see is that kind of reddish pinkish line. So if you look at the cone light adapted sensitivity, so our cones are giving us more acuity and ability in the light to see. And then we turn off the lights and the red curve, the pinkish red curve starts, and they dark adapt. So their threshold is getting lower and lower, which means their sensitivity is getting better and better. And this is something that I probably need to walk through a couple of times and keep reminding you about, is that as we're going lower on these curves, sensitivity is getting higher, which Goldstein has shown with the high at the bottom and the low at the top, those words that we're talking about sensitivity there. What we're measuring with the dark adaptation curve, we're using the method of adjustment to measure threshold. And as my threshold for being able to see this gets lower and lower, my sensitivity gets higher and higher. So for a while, we see their sensitivity gets better and better, their threshold gets lower and lower, and then it has this kind of leveling off. Okay, and this is really happening about 6 or 7 minutes out. This leveling off occurs, and at about 8 or 9 minutes, we start to see another bit of adaptation where their sensitivity is getting better and better. Again, I'm following this kind of pinkish red line until we get to this dark adapted sensitivity at the bottom, where we're really at a pretty high sensitivity, pretty low threshold. Okay, if you remember, this is a person who starts out in the light, the cone light adapted sensitivity. They're adjusting that flashing light in the periphery, and this is as low as they can get it and say, yes, I still see it. We turn off the lights and we see that pink curve, and that's the basic dark adaptation curve that any of us would see if we did this kind of study, or when we walk into a theater, that kind of dark adaptation. Okay, we're going to show how this is really both the rods and the cones, and the rods and the cones each have their own part to play in this dark adaptation curve. Okay, so I'm going to start with the pure cone curve, so the green curve. What we see there is this, they get better and better. We see this leveling off, and it stays leveled off, right? They stay there. After the 6 or 7 minutes, they don't get any better. The way they found this curve is the person looked at the fixation cross or whatever, fixation point, and the flashing test light was right there at the fixation point. So we are now testing that flashing test light at their fovea so that we're only influencing their cones. And we see the maximum cone sensitivity is not quite as high a sensitivity as we can get. It's kind of somewhere in the middle there. Okay, I'm going to go through the rod curve. So now we get people in there who are actually rod monochromats. They have no cones in their retina to begin with, and when they are born. And so we test them. And if you notice, their rod light adapted sensitivity. So the lowest that they can get that flashing test light is not very low, and it's not as low as a person with a cone light adapted sensitivity. We start to test their rods, and we're gonna turn out the light, and in their periphery, they're going to use the method of adjustment and just turn this knob until they can just see, and they can just see, and they can just see that flashing test light. And we can see the blue curve now. Okay, so for a while, even those of us with rods and cones, the rods were sensitive, but they weren't as sensitive as the cones. So we didn't see any influence of those in our dark adaptation. But these people who are rod monochromats, we can see that they have this really slow and steady curve where they can lower that test light and lower that test light, and their sensitivity gets better and better. And it's a smooth curve from the beginning all the way out to about 20 or 30 minutes where they get at their best, where they can get at their highest sensitivity, the lowest threshold. And it really matches those people who are using both the rods and the cones as they get to their out to 20 or 30 minutes. Because if you go back to that previous slide of those, the regeneration time is about 6 minutes for cones and about 20 to 30 minutes for rods. And so this really describes this curve and how rods and cones are both playing a part in that dark adaptation, and why it takes us really a good 20 or 30 minutes before we are very well adjusted to the dark. And I'm running a little over time here, so I'm going to stop at this point. So I had this experience with my niece, and it's kind of funny. So I always hope to strike you guys as funny sometimes. But where we were driving at night, and someone came in the opposite direction, and they had their bright lights on, and I'm driving, and I did this. Oh, you're bleaching out my rods! You're bleaching out my rods! And I started screaming. My niece thought it was hilarious, but really, it's going to take me a while, right? It's going to take me a little while just to get to any kind of dark adaptation and be able to see again. But it's going to take me a good 20 minutes to really be able to see well. And I think as I get older, that becomes more and more of a source of anxiety when I can't see at night. I keep coming back to this summary slide because I do want it to be sort of at the beginning, at the end of these videos, of reminding you that what we're talking about are the rods and the cones, and we're going through the differences. We've seen physical appearance differences, differences in distribution across the retina, the wiring, and I'm going to actually get back to that wiring and how it affects acuity and sensitivity after we talk more about neural processing specifically. And we've talked about the clinical issues, and we started talking about functional significance. So there's just one more tiny piece to talk about color vision and what the cones give us, but I need to wait to do that. And this is the kind of just the summary for where we are right now, so that we can talk about color vision and then move on to neural processing.